impressed us so much. It was such good fun. It was showing us IoT devices, but more importantly, talking about how vulnerable they are. And we're going to see a lot of, hopefully, much more of that tonight. I'd like to welcome Tony G and Andrew Tierney from Pentest Partners, who are going to talk about that little webcam down there on the desk. That's the source of potential problems, and they'll describe to you how it works, and more importantly how it doesn't work, and the dangers of that. For those of you who are watching this live broadcast, let me know the weather in London is very cold, so you're probably better off sitting on your sofa watching this. The next Hackfest event, which we're also supporting, is on 24th of February. It's on cyber risk and liability for company directors. It's not truly an internet topic as such, but we do support Hackfest. At the end of the event, there is food for people who have paid for food. You've got the badges with the green highlight on. Headquarters thought it would be a good idea to highlight them in a dark green over a black text, which means they're totally unreadable now. There was no system testing beforehand on them. There's quite a few of our committee here tonight. Apart from myself, we've got Colin, who's also very involved with the broadcast. He's normally our treasurer. We've got Christopher East, who's our honorary secretary. He's the man at the back running the broadcast. We've got Randy, She, Neil, Jane, Kavita, and hopefully Peter from our committee. So, without more ado, please enjoy. Just to say, if you don't want to be in the broadcast, because live broadcast, we have to tell you that you should sit somewhere over that side, right at near the wall. But you have over there. If you're having to be live on Britain's Got Talent, then please stay where you are. Ladies and gentlemen, Andrew and Tony. Thank you.
Brilliant, thank you very much. Hopefully you can hear me through this. I can't shout anyway, so hopefully you can hear me. So my name is Tony G, and I work for Pentest Partners, and we're ethical hackers. And but in our spare time, we kind of hack apart some IoT devices, and that's kind of what we're going to talk about today. But I'll let Andrew kind of briefly introduce himself, and then I'll kind of go on with the start of it, and then we'll switch over to him, and he can show you how we actually hacked that Samsung camera just down there.
Yeah, so I'm one of the security consultants at Pentest Partners. I kind of specialise in IoT. I did an electronic engineering degree, so it's kind of closer to what I actually studied at university. We do a lot of this in our spare time, but we're also starting to get a lot more work coming in terms of IoT. And what we want to kind of get across to you today is how we hack these devices, what we actually do to them to hack them, so you can kind of learn a little bit about how you hack them, but also the risk that they present to networks. So a lot of IoT research doesn't really get the risk across to users. So that's kind of what we want to talk to you about today. Cool.
So what is IoT? So a lot of people think, IoT is a device, right? It's just this individual device. But actually, IoT is kind of a network of connected devices. It's not just a specific device. But for this purpose, though, IoT is not just internet connected. It's Internet of Things, but not just internet connected. It doesn't always have to be smart either. You might have a standard, simple device that just does stock management within your building, your manufacturing plant. It doesn't necessarily have to be hugely smart and hugely technical. And it also doesn't always need to rely on masses of data. But it is very complex. So let's start by what most people kind of think is what makes up IoT. So we've got a thing, and whatever it is, a device, right? And that often connects up to some kind of a cloud-based service. And so when you come to attack this, you've got an attacker. They're going to attack the device, right? And they're also probably going to attack the server. That's your basic view. But the thing is, we kind of know how to look after servers. So most of our target is going to be focusing on the actual device itself. But that's a naive view. The actual view is actually very, very different. So yes, we've still got our thing, we've still got our device, And that's going to connect to some kind of a cloud infrastructure. But then you've got a user of the device. Then you might have the segmentation, so you've got the device on the cloud, so that's on their service, then you've got the actual internet in between that. Then you've got your router, that's still part of this ecosystem. Then you've got the router at the server side. Then you've got the users, the other users on the network as well, and then you've got users on the internet. You know, a lot of these systems have got cloud-based connectivity that you can just connect to directly from your mobile phone. Then you've got actual internal users. So you've got users internally to the cloud system, to the service provider. So that might be, you know, your HR systems. It might just be IT support systems. It might be other marketing type people. But then you've also got routers along the way. You know, the internet's not made of just a direct connection between lots of computers. There's lots of different hops it steps through. And then you've got backup systems. Then you might have support services from the cloud from the cloud that you've chucked all of your systems on, your back-end systems. And so then when it comes to kind of attacking it, where is it? There we go, got there. When it comes to attacking those systems, you've got different ways of attacking it. You could attack the application itself, so the end user, using the web application, the mobile application, the actual physical device itself, or just attacking the network infrastructure. You might have malicious insiders who are inside your network targeting your systems, or just a hacker inside your network targeting your systems. You might have someone having a man in the middle position targeting, you know, between your cloud infrastructure and, you know, your endpoint, whatever that happens to be. Then you might have someone targeting you as the supplier directly, whether that's directly from the internet or whether it's targeting users, or perhaps either internal to you or malicious insiders within with your cloud service provider. And then you might also have governments who are targeting the actual network infrastructure itself. So you can begin to see it's actually quite a complex setup, especially when you start to think about routers. And IoT is a little bit different to normal internet, so normal devices, I've kind of explained. And this device, I think, perfectly illustrates how a simple mistake can actually have quite far-reaching consequences. So we had a look at this quite a few years back now, actually, and it's just a standard car park terminal. It was connected to the internet through some kind of GPRS connection as well, but also on the back of it had an Ethernet connection. And so you could just unplug the cable and plug into a laptop. And who's going to challenge you? If you turn up with a laptop and sit behind a car park terminal, no one's going to challenge you.
I think I sat there for 45 minutes before scanning the network on the floor. This isn't actually the machine, but I sat there, no one said anything to me.
It's nuts. And when we think about IoT devices, they have zero, in a lot of cases, user interfaces. You know, this Samsung SmartThings device, the only interface that it's got to interact with the end users is 3 tiny little LEDs on it. And that is it. So there's no real kind of user input area. When we talk about IoT and the growth of IoT, you know, there's a lot of kind of hot air in terms of how much it is growing. We don't really know how much it's growing, but what we do know is it's growing quite a lot. But the biggest problem, I think, with IoT is actually its users. A lot of users of IoT are just non-technical people. You know, think how many of your friends have bought some kind of a smart device. Maybe it's a Hive that British Gas have sold them, or maybe it's some kind of smart light bulbs from Hue, or perhaps even an Alexa, Amazon Echo. You know, they're not technical people. They aren't necessarily going to understand the technical workings of that device. And then if you think about CCTV cameras, for example, and other IoT devices that you're installing within your business, you're going to have some kind of an installer do that. And I think the Hive perfectly illustrates that. You know, your British Gas engineer comes round, he's a plumber at the end of the day, or a gas engineer at the end of the day. He's not necessarily technical. He may not even have laptops and technical equipment to actually interrogate the system properly. He'll probably have a very scripted install process. So he's not really going to understand the technical details of it. So, as I say, IoT is very different, and we've got a lot of new challenges with IoT. In terms of, you've got things like, where it's deployed. Often these systems are deployed in physically insecure locations, like that car park system. You might have other challenges like that they're always on and always accessible by anybody potentially. And I'll tell you what, I think you've probably already read that. I'm going to hand over to Andrew, because Andrew's going to talk about how we can actually hack this Samsung camera, which I think is probably more important than me talking about it in a little bit.
Right, so we're going to talk about hacking this little Samsung camera here. Now, we bought this a couple of years ago off the internet. Oh no, actually it's from PC World. It was sold along the Smartphones Hub. I bought it because it looked interesting. And I thought, I hack it. I tried to find out the vulnerabilities in this device. And what I'm going to do is I'm going to take you through how we hack this. It's still for sale. It's available on Amazon. It's quite expensive, £110, and it still has vulnerabilities in it. When you get the camera, it very much encourages you to use an app on your phone. So you go to the Google Play Store, download an app, it will connect through the cloud, through to the camera, and you can view your images. That all works fine. But what we did was we port scanned it. And when we port scanned it with Nmap, what we found was it had several ports open. So it's got port 80 and 443, which are web services, port 554, which is called RTSP, which is used for video. It had port 1022, which is curiously 1000 above port 22, which is normally used for SSH. It also had 49152, which is for UPnP. Now, considering this connects through the cloud, why does it have to have these services open on it? We weren't really sure. Now, what I'm going to try and attempt to do during this is actually show you us doing this live against the camera that's connected to my laptop. Now, I can't guarantee it's always going to work, but we'll give it a go. So here we've got a terminal window. Hopefully you can see some of the font there. It's about as big as it will go that it's still containing enough information. So we just port scanned it, and again, as you can see, we've got the same ports we saw open earlier on it. Nmap's a brilliant tool. It's free. It's probably the first step on any device we try to hack to see what ports are open on it and what they do. So what we want to do is, now that we've seen that web ports are open, we want to visit it in a browser. So that's what we did. We went to it in a browser, and you get this password prompt come up. So it says to access the camera, enter the private key for the camera you selected. Now, I didn't know what the password was. The documentation had absolutely nothing in it to do with the password. So I just typed a random password in. What we can see, I skipped ahead a bit there, but here's the first one of IoT devices, is that these things are running undocumented services. So this is running web, SSH, RTSP, and UPnP for absolutely no reason. You could just shut them all off and the device would be a lot more secure. Now when we're messing about with devices like this, we use this tool called Burp. Now it's a bit of a weird name, but what Burp does is it sits between the browser, the web browser, and the device and intercepts all of the requests and lets us see what's going on. So the list at the top here is all the different requests we're making through to the device, and down the bottom it actually shows us the request going from the browser through to the device. And inspecting the traffic like that quite often gives us really, really kind of strong hints towards vulnerabilities in the device. So when we type in a random password, we get this prompt come up. So it says there's no private key installed. Now when it says private key, it means password. It's a bit confusing, but it's the terminology it uses. Please create a new private key. So when we look at that in the background, you can see this is the request on the left-hand side and the response on the right-hand side. What it's doing is making a post request. So it's posting a piece of data, saying check, then the password, and sending it to the device. And when the device gets that, it realises that there is no password. It's never had a password set on it before. So it says, it responds, it says no key. And that causes the browser to respond like this. So it asks us to set a password. So we've already got a problem there. If you haven't configured a password on this device, anyone can connect to it and set the password on it. So you're unaware of this user interface. You're using it through the cloud. You're not aware you can connect to it. So what we do is we set a private key. And what you can see in the background here is you can see that it's sending new, and then the password I set, BCS IoT20, and it's sending it through to the other end. So that's how it sets the new password as a post request. Once we've done that, we've logged into the device. So we've now got access to it with our new password. That's everything as expected there. However, there's a bit of a problem here. When you log into the device, what it does is it receives the password. When it says check up the top here, it receives the password and it compares the password to the set private key. If the two are the same, it will allow access to the device. This is as expected. You need to know the password to get onto it. However, when it sets the new password, as we saw earlier, as you can see the new keyword up there, it doesn't check that there's already been a password set to the device. It doesn't check to see if the password is correct. It just accepts the password. So what this means we can do is we can just send to the device a new password, even if a password's been set. It's that simple. That is how we reset the password on this device. So I'll just show you how that works. So back to the terminal prompt here, and I'll pop up through my history, and hopefully it's there. Get it up on here. So yeah, this is just using a utility called curl, which just makes web requests, so it's a post request, and that goes away to the camera, so it's wrong IP. Right, they're nice.
It's fine, it'll be alright.
So yeah, make that request, and that's it. It's changed the password on the camera just by making a single request like that. So we've got quite a big problem here. You really shouldn't be able to change the password on a camera when it's already been set. So this is a logical flaw in the way that you set the password. Now the thing is, this was found very, very quickly. A half day's worth of pen testing would have found this problem. So code review as well. If you'd read the code, you'd have seen that the request to set the password didn't check if there was a password set. It was quite an easy problem to find. Now the thing is that someone had reported this vulnerability to Samsung in 2014. So a whole year before I got hold of this camera. A whole year and a half before I got this camera. It was in a slightly different camera. So they fixed it in that camera and didn't bother checking all the rest of their cameras for the same vulnerability. So this problem existed across loads and loads of other cameras, and they just hadn't checked to see if it was in the other ones. So when someone reports vulnerabilities, actually fix them. Look across all your products and say, we might have made this mistake somewhere else. Now the thing is, with that, all we've got is access to the web interface. Now that's not great. We can view the video, we can reconfigure the device, but we don't have complete control over it. And we want root access, we want complete control over this device. There is a problem with the web interface. It only has one user. It's got an administrator user, and that's it. So if you're using the camera in the real world, most of the time people just want to view the camera. They don't want to change the network settings, they don't want to reconfigure it, they don't want to update the firmware. But this only allows a password, there's no user. So if you get access to the web interface, that's it, it's game over in terms of that functionality. You'll also notice one other thing, is that at the top there, it's just using HTTP, no encryption. So if you visit the normal web interface, it doesn't redirect you to the secure one. So anyone can sniff your credentials. So if you're using this over the internet or even in your house or in your business, people can see what you're sending to this camera. So they should use HTTPS on this, but they don't. Now, when we're looking at something like this, if we want to take it from just access to the web interface to root access, it's really, really helpful if we get hold of the firmware. So the firmware is just the software running on the device. Now, it was quite easy for these guys. We just went to their website and we downloaded the firmware. Interestingly, in response to us reporting these vulnerabilities, one of their things they did was stop you downloading the firmware off the website. Maybe not a great idea. They've left it up for all of the other ones, but it's missing this one. So we downloaded the firmware. It's just a tar.gzip file, so we can unpack that. And within that, we've got a number of different files. Now, they've got weird extensions, WM3 and so on. There's a utility in Linux called file, and what it does is it has a guess at what's in the file faster. So quite often this works. If it's a zip file, if it's an ext2 file system, it will tell you. Here I run it in this file and it comes up as dbase, dbt. It doesn't really make any sense. So we need to work out how that file's structured to unpack it, to turn it into a file system. So this is a really brilliant utility called binwalk. And it's quite simple. All it does is it steps through a file looking for magic signatures. It just looks for series of strings. And the first thing it does when we run it against one of these files is it finds a signature for what's called a YAPS file system. This is an embedded file system that's quite often used. It's read-write, it's very common. But binwalk also unpacks all of the firmware. So we can access it where it's as if we're on the device. So we can access all the scripts, the web interface, all the binaries, everything on this device. We now have access to it. So we can examine it and see how it works. So what we've done is we've taken what we call a black box pen test, where we're looking at the device purely externally. We've taken it to somewhere between grey and white box, so we can inspect the operation of the device. This is really, really powerful for us. It's important here that the firmware is easy to obtain and unpack. Now, I think they should make it harder to unpack. Now, some people call this security through obscurity. Now, security through obscurity is the relying on obscurity to secure your system. It isn't using it as part of your security. So security by obscurity is bad, but security with obscurity isn't. So if you encrypt your firmware, ultimately the camera does have to decrypt it to install it. You can reverse engineer the way that it decrypts that. It will take you more time, but what it does is it stops people like me messing about with cameras they bought at PC World the week before and finding vulnerabilities in the space of hours. It makes a big difference, I think, anyway. So once we've got access to the device, we can just view the files. Now, I don't know how many of you know how Linux stores user accounts and passwords. There's a file called password and there's a file called shadow. And in the shadow file, it lists all of the users and it's also got the password hashes. Now, looking at this file, which is shown on the screen, you can see there's only actually one user that does anything, root, up at the top there. The root user is the super user. I'm sorry if this is all obvious to you, but the root user is the super user. What that means is the web interface on the device is running as root. The RTSP service is running as root. Everything on that device is running as the root user. So if we compromise the web interface, if we compromise the RTSP server, we already have complete control over the device. There's no need to escalate privileges from the web user to root. So they could fix this. It's quite easy. Follow the principle of least privilege. Have a specific user for the web interface. Give them limited permissions, so you can't break out of the web interface and do anything serious. That wasn't done. Now, you see the string next to root that starts with Y99. It's called a password hash. And what you do when you store passwords on these systems is you hash them. And what hashing is, it takes a word, or a variable length string, performs a transform to it, and produces a fixed length output. Now the idea is that you can't go from that fixed length output back to the password. So you can see slight changes to the password here, say capitalising the P will completely change the hash. Putting a 1 on it will completely change the hash. The idea is that it makes it difficult for us to work out what the password is. To check the password is correct, all we have to do is perform the hash against the password we provided. It's a very common way of doing things. Now, what's interesting about this hash is it's really, really short. You'll notice it's only a few characters long. It's called descrypt. Now this was the original Unix password hashing mechanism, and it's got one very, very interesting limitation, which is the passwords can only be 8 characters long. So I think you'll probably all agree, an 8-character password isn't long enough. Now, what that meant we could do, with 8 characters, we could perform a completely exhaustive search of every single password for that hash. So normally when we try testing passwords against hashes, we use dictionary words. That's how most people form their passwords. We've got a big long list of passwords. We have numbers at the end and so on, but we won't do an exhaustive search. With descrypt, we knew it could only be 8 characters long. With our cracking rig, which is a powerful machine with lots of graphics cards in it, we could test all passwords. And we quickly found that the password, the root password for this device, was this string here. Now, we haven't previously published this, but it's been out there for a while now. What was interesting about this was we downloaded firmware for other Samsung cameras, lots of other Samsung cameras, and they all used a password hashing mechanism called MD5. Now, first off, that allows passwords to be of unlimited length, and it also is a lot slower to brute force. We're talking about an order of sort of 15,000 times slower to brute force compared to Desperate. If we'd have got the MD5 hash off another camera, we probably wouldn't have got this password. It would have been too slow, and we wouldn't have tried the exhaustive search of 8 characters. We'd have gone for longer passwords with dictionary words. So, yeah, don't use weak password hashing mechanisms. Use the strongest one available to you. They could have used MD5. It's all available on the system, so we're not sure why they didn't. Now, we still haven't got root access via the web interface. So we could log into the device via SSH with that password. That works. But what we want to do is we want to go via the web interface that everyone can access on your network, and we want to get root access from that. So we've got access to the firmware. What we do when we have access to the firmware is we just search for common strings. So we look for files containing debug, we look for the word password, the word root, things like this. And it's really quickly found that with 3 files with the word debug in. So one of these was called debug CGI. And it was in the directory that serves web files on the device. So in the browser, we visit the address debug CGI, and we get a response back, ng. Now, I don't know what ng means, but it means that that script is responding to our input. We're able to access it, which means that if it's got any vulnerabilities in it, we can exploit them. There's no need to have this debug functionality in these devices. No one, so users don't know about this web interface to start with. They're not going to know about this hidden debug functionality either. These cameras that are out there, no one's going to be using this functionality. Why is it there? Get rid of it. So what we want to do is we want to take that executable file, debug CGI, and we want to work out what it does, find vulnerabilities. The way we go about that is called, well, first off, we disassemble it. We take that file, we load it in something called either. What that does is it reconstructs the program flow from the executable. It's still assembly instructions, but it's much more readable. We get a nice graph, as you can see here. Quite quickly, something really interesting jumps out. We see Linux commands within the strings contained within this file. So this is gunzip, which unzips gzip files. You can also see %s%d. Now this is passed to a function called snprintf that substitutes other strings in there. So we're taking a command, we're substituting strings into it, and then we're running it. So this suggests command injection. The command injection is when a user can pass input through to a device and then run commands of their choosing. We hadn't quite found it at this stage, and through a process of trial and error, we actually worked out how this debug CGI script worked. Sorry, it's getting a little bit small. So, what you do is you pass it a few parameters. First off, n submenu equals shell. So that's quite obvious, it means run a shell command. After that, command equals netstat. Now what it would do, it would take certain commands. So it would take netstat, ifconfig, which tells you about the interfaces on the device, and a few other bits and bobs like that. But it was a whitelist of commands, so we couldn't run arbitrary commands, so we couldn't really take control of the device. However, one of the commands was ls, which is list all files. To tell it where to list the files, you have to pass it at the end here a command argument. So command argument / shows us the root directory on the device. This is starting to look like command injection is going to be quite possible if they haven't adequately sanitized that command line. So what we do, we put a semicolon. And in Linux, when you put a semicolon on the end of a command, it means, okay, once I'm done with that command, run another command. So all I do is put semicolon, who am I? Who am I just tells me what user I'm running as. As you can see down at the bottom here, we've now got an output from that command. So now what we're able to do is we're running commands, arbitrary commands, on this device as root. So we've almost got complete control of it, but not quite. It's not quite there yet. So we want to be able to run more complex commands. So let's try and read out the password file from the device. So at the end of it, we put cat space etc password. Now the problem is when your browser gets a space in the address bar, what it does is it URL encodes it. So it changes it from a space to %20, so it gets transmitted correctly. The device doesn't like that. It takes that %20 and it literally puts it into the command. And then it says, no, I can't run that. So we can't put spaces in the commands. That's a bit of a limitation because most commands that you want to do anything with, you're going to have to provide parameters. But we can work around this. There's this really neat little trick, and if anyone in this room can tell me why this exists in shells, I'll be impressed because no one's told me that. In most Linux shells, you can put curly braces and then put the parameters one by one, separated by commas, and it will put the spaces in automatically. It's called brace expansion. So cat, etc password will expand out to be the command we want. So now we can do whatever we want with this device. We can run whichever command we want. So there's the password file. But we still haven't really kind of taken complete control of it. So yeah, you need to sanitize your user input. It's really challenging when you're passing things through to a shell command to only accept valid parameters. In reality, they should just not have it there in the first place. So we turn this into a script. And this script's pretty simple. The first bit of it, what it does is it carries out that original attack you saw. So that original attack was changing the password on the device from one that we don't know to one that we do know. That allows us to access the debug CGI script. Once we've got access to that, what we do is we read out the shadow password file. We find out what the root password hash is, just in case it's different to the firmware we've got. And then we just perform a search and replace in the shadow password file for a hash of our own choosing. So we change the password to root just by doing a search and replace on a file. And from that point, we can SSH into the device. So I'll show you that on the actual screen here. So it's a really simple script. If I can type. So yeah, it's just a Python script. It's got a lot of comments in it. This is available on our GitHub if any of you have these cameras at home, so you can play about with them. Break your own camera. Yeah, I just run Python samsung.py. Again, type that in there. So that'll go away. It makes all those requests. That's how quick it is. We've now changed the root password to be root. So now what I can do is I can SSH. So root. They put it on port 1022 just to keep the hackers away, and it takes a second or two, asks for the password, and we're now on the device as root. So we can do what we want to. So we shouldn't be able to do this. You shouldn't be able to go from a web interface on a device, change the root password, and then log into it. If this was on your business network, it would mean that anybody with web access to the camera, which is quite a common thing to do, you know, the security guards or a manager wants to be able to view the camera, they can get root access to that device, take control of it, and do as they please. And it's sat there on your network. You've got no idea what it's doing. You've got no way of telling what's actually being compromised. So it's quite scary, really. So yeah, this could have been fixed in so many ways. Get rid of most of those vulnerabilities, and we wouldn't have been able to chain these attacks together from start to finish. Code review, pen testing would have all fixed these problems, but none of them were done on this device. I'm going to hand back to Tony for the next.
Cool. Thank you. So yeah, it was pretty easy, right? Really, really easy. I know obviously there's quite a lot of technical stuff there, but actually, when you look at the attack, it was all pretty basic stuff that we did there, basic stuff that would easily have been detected through some kind of a penetration test or some kind of code review on there, as I've said. But what I wanted to do is I wanted to talk about your networks and whether or not we think the network is a nice, safe place, our own internal network. And the reality is, it's absolutely not. Quick question, quick show of hands. Who's changed the Wi-Fi password from their default Wi-Fi router they got from their ISP? Good, I'm really glad of that. We are in the BCS, so you'd expect that to happen, but actually there's a lot of people who didn't put their hands up. What about your admin password for that? How many of you changed the actual admin password for your router? Less people.
Pretty much the same, very similar.
There's a little bit less. Ooh. What about updating the firmware on it? Definitely a few less there, right? Do you allow other people on your network? Your friends, your family? Have you got a different guest network, or have you got your own, you just give them your password?
Do you not let your family into your own network?
No. I'm afraid no. It's just for me. So how many people let their friends and family access their own internal networks? You have no guest network or anything like that?
Yeah, but not for the family.
Not for the family. I'm fair enough, I'll give you that. Have you got the capability to detect intrusion on your internal network, your home network? Anyone got that?
Cool.
5 people.
Does anybody run Snort? Yep. There's 2 of us.
So there's 2 people. And that's it, because who does that? Who, apart from Andrew and the 3 people in the room, who actually detects intrusion on their network? No one does. The problem is though, routers nowadays are really, really dangerous. Every week, virtually, we're seeing a new vulnerability identified in some new router, whatever that device happens to be. And a lot of them are pretty serious vulnerabilities. But it's not just that. When you look at the actual passwords, the default Wi-Fi passwords, you guys have all changed them, but a lot of people who are installing this stuff on their home network, they won't have done it. They've taken the card off the back, they've taken the password, and they put it back in, and that's then done for the day. And so, when you look at the actual PSKs, it's pretty easy to break a lot of them. You can see on there, things like Orange, for example. It's really easy to guess that. We estimated with our cracking, we're in about 5 minutes to crack that passcode. When you look at sort of the BT home hubs, it gets a little bit more complicated up there, but still only days. And all I need to do is capture your handshake once, and then I can walk away, and I can then crack that at home. And then come back the next day and try and gain access to you. Did anyone see our research into the Mitsubishi Outlander? So I'm not going to go into the detail on this, but this really illustrates how important your PSK is on your Wi-Fi network. So the Outlander's got a Wi-Fi network, as I'm sure you're aware of, right? If you read our research notes. And it's got a Wi-Fi network. The SSID can be changed, but the password can't, which is a bit dumb. But that's what they've chosen to do. It is really, really poor. It's a really poor password. It's something like 6 numbers and 2 letters or something ridiculous like that. Really, really easy to guess. And so it's quite easy for attackers and for us to crack that password. And then, of course, we were able to unlock the car, which is obviously not ideal at all, because then we could steal it, which is bad. But when you think about your internal network, you've then got things like port forwarding. How many of you got ports open on your network that you've forwarded through? Maybe you've got technology that needs it, like who's got an Xbox, for example. How often does a UPnP that you might not, for some ridiculous reason, enabled? How often does that not work and you have to forward through some ports to it? So how do you attack port forwarding? Well, in a normal way, what happens is you open up your firewall, right? And then you can connect through to it, or whatever the service is that you've opened up that port for can connect through to it. And an attacker, normally they'll try and connect in, they want to try and connect into that computer, so they have to go through your firewall, but they're not going to be able to. But what they could do, if you've got one of these smart devices which have got some kind of port open, rather than trying to do that, they just attack that smart device, like the camera, for example. And then they can get root access on that camera, and then they can start to own that, and then they can start to own your other devices internally. And it's just a simple case of that port forwarded being open allows us to access it. Andrew said, how many you might have port 80 open because perhaps that's what's required for that camera for you to be able to access it. So I'm sure people who've got CCTV cameras at home, they might have a connectivity so that they can access that camera from their phone when they're out and about, right? So you can see whether someone's burgling you. Well, if you've opened a port for that, the attackers can use that. If they can exploit the camera, then they can use that to exploit the rest of your internal network. It's really, really easy. And that creates a bit of a problem when we think about Mirai. Mirai is, I think we're all probably aware of Mirai, right? Everyone aware of Mirai? The botnet that attacks CCTV cameras and DVRs? Anyone not aware of it? Wow, really? This is BCS. Come on, do your research, seriously. So Mirai was a botnet of computers which a piece of malware which targeted and created a botnet of smart devices, primarily CCTV cameras and DVRs. And they were used to create massive denial of service attacks against other networks. And they actually knocked Twitter offline by targeting the DNS servers for Twitter. And the thing is, that occurred quite simply because the devices had Telnet running on them. And some people had enabled that through UPnP or through port forwarding to be able to be accessible from the internet. And Mirai took advantage of that, and as a result, it was able to control those devices. Now the problem is that the manufacturers of those devices didn't really care. They weren't really that bothered about fixing it. And there was very little that you as an end user could do to fix it. In fact, there was pretty much nothing. Hang on. Pretty much nothing that you as an end user could actually do to fix Mirai. Because the file system of these devices that were being attacked was all read-only. So you had to get the manufacturers to fix it, and in a lot of cases they couldn't really be bothered. And when you kind of throw cloud infrastructure into it, it gets a little bit more complex. So complex that I'm not going to do it. I'm going to ask Andrew to do that bit. You're welcome.
So the alternative to port forwarding now really is what we call cloud connectivity. So instead of connecting into the device from the home network, the device connects out to the cloud. Once the device is connected out to the cloud, the user then can connect to the cloud to get the connectivity back to it. So it's quite a common pattern to see now. The attacker comes along, he wants to get to your computer, he has a crack at your firewall, he can't get through, there's no porting, so it should stop everything. He has to go to the servers, but the servers, we know how to secure these servers, so we've secured them properly. Central monitoring, logging, everything like that means they're less likely to be compromised than the individual device in your house. So how do we attack devices and computers inside the home network once cloud services are in use? Well, there's quite a few different ways. Now, I'm going to explain something that we call, everyone calls cross-site request forgery. Has anyone heard of this? Okay. So a few people have heard of cross-site request forgery. So you're a user sat there browsing the internet, and you make a request through to animalpics.com, and you want to load the page catpics.php. So you make a request through to that server. The server returns a bunch of HTML to you, and that may include links to other websites. So here it's going to the site catpics.com to load kitten.jpg. So now your browser, completely normally, this is absolutely standard on the internet, and what's meant to happen, we'll go to catpics.com and make a request for kitten.jpg. It will return kitten.jpg. So now you've viewed an image, it's embedded into the other site. So this is a completely normal part of how the internet works. It's expected. But we can do bad things with this. So now we're going to go to Animal Pics and we're going to try and load catpics.com. Now instead of loading kitten.jpg, what this does is it tells us to load another image. It's facebook.com/update.php, password equals ABC123. This is just an example. It's not actually an image, but it's going to make that request nonetheless. The browser does not care what that is. It's just going to make that request regardless. So if we go to facebook.com, it will make that request. The other site won't be able to see the response, but unless you've protected against this, that request will be made and it could be active. Now we can use this against devices on the home network. So I'll show you how we do this. This is some JavaScript. It's automatically generated using Burp Suite, so it will generate cross-site request forgery requests for you. What it does is it's making that original request we made at the beginning to change the password of the device. So it's JavaScript, you can see at the top here, it's making a request through to the IP address of the camera, posting the new password, BCS IoT20, and then it's submitting that automatically through to the camera. Now, this actually live see if we can get it working. So we've got a web browser here. So let's just check that the camera's still responding. Yeah, I think the camera's still responding. So at the moment the password's admin, so I'm going to log in with admin. Yeah, so we're still logging in with admin, the password's as expected. So what we're going to do is we're going to go to my dodgy website. So that's eor.io/samsung.html, and we load that. Now what's happened in the background here, if we bring up the inspector and look at the network, reload the page. Sorry, let's do that again. By the way, if you ever see eor.io in your logs, be worried. So yeah, we can see it's made that request. I realise this is small. It's made the request through to the camera, so you can see the IP address there, 192.168.2.4. It's changed the password on the camera by us visiting my website. So that's quite a serious problem. Just double check that. If we come back to here, you're just going to have to trust on typing the actual right password in rather than just tricking you. But there you go, BCS IoT 16. And there we're logged in. So we changed the password by visiting another website. Now these cross-site request forgery vulnerabilities are quite common. Now some people might say, how do you know the IP address of the camera? Well, there's quite a few ways for us to know what the IP address of the camera is. How many of your networks are on 192.168.0 dot whatever? Or 192.168.1? So not all of them are like that. You'll notice that in these scripts it's different for me. There's a reason behind that. But what we do is we just guess. We just try every single IP address. So this is on my 192.168.4 subnet. Just have a for loop running through all 255 IP addresses, just spamming it out. So loads and loads of requests will fail. But the browser, it doesn't make any difference. No one will notice. So you can see here in the inspector how it's going through trying all the different IP addresses. The top one here, it's my router, and that says redirects you through to the login page. Down the bottom here, the 15, it's the camera, and we get 200 success. So again, we just spammed it across the network. Now we've changed the password. On this camera, we can't actually do the rest of the command injection to get full access because of some technicalities with it. But what we found is this very, very cool attack. Oh, I think this is cool anyway. So this is how we attack your devices behind routers when you're using cloud connectivity. So we've got a device that connects through to a server. It does that for communications, for firmware updates. In this specific example, it's firmware updates. We've got a user sat in our house, and he likes browsing the internet. He likes viewing random web pages, and he's not very careful about links he gets in emails. So our bad guy comes along with his bad server, and what he does is he sends a phishing email through to the user, and it's got a link in it, and that link is a web page that does what I've just shown you there. And instead of attacking the camera, what it does is it goes to your home router. And it makes a CSRF request to that home router. Now routers are even better, because they normally reside on 1 or 254. There's a brilliant bit of functionality in Chrome and Firefox called WebRTC that allows JavaScript to determine what your local IP address is, so we don't even really have to guess at the subnet, so even if you've changed it, we can still find it out. Now, that CSRF request tells the router to change the default DNS servers that it's using. So normally your router will be using your ISP provided DNS or Google's DNS, 8888. We tell it to use our DNS. Now once we've done that, every time your router resolves an issue, we have control over which IP address you go to. Now this is a bit of a problem when it comes to things like banking websites or Google. You'll get warnings all over your browser. You can't even visit Google if the certificate doesn't match because it's pinned in Chrome. It uses a few other technologies that makes it very difficult. However, your little device sat there on the network uses HTTP to do firmware updates. So we redirect it through to our server. It downloads a malicious firmware update. We now have control over the device behind the network. That can then be used to attack the users on the network. Now this sounds pretty ridiculous and a pretty complex attack, but in a kind of, I'd say a representative sample of home routers, we found about 25% you can change the DNS servers via CSRF. This was actually done in Brazil, which has a virtual monopoly on ISP. There, it's just one ISP really. So all the routers are homogeneous, which means that a single attack against those allowed the DNS service to be changed. An actual fraud was carried out as a result. This is one of my colleagues. He's done a similar attack against another camera. So this uses a different attack vector. Has to use iframes. So each one of these is a little frame for each IP address. So it does it for all 255 IP addresses. It carries out an attack against the device. When it succeeds, what it does is it makes the camera FTP images from the camera through to a server under our control. So now we can see what's happening on camera just by you visiting the website. And it doesn't have to look like that. It can be completely hidden. How are we doing for time? So yeah. How do you resolve CSO? It's actually really, really simple. You have to check that the request is coming from the device. So when you send a request from my website through to the device, it will say that the server it's come from is the email.io. The device just said, has the request come from 192.168.4.15, which would be itself. If the request has come from itself, allow it to be carried out. That's the most simple way to prevent against that. There are more complex ways of doing what you need to do, and you've got more involved applications, but for embedded devices. Of course, you could disable the web interface that no one's going to use, so make it easy. I'm just going to talk another quick attack. Has anyone heard this kind of mantra, physical access means game over? So it's quite common. It means if someone nicks your computer, it's game over. They can get data off it, they can do what they want. Encryption and stuff's making that more difficult, but the important thing with IoT is you've already given the attacker the device. So we went out and bought this. So to examine the firmware on this, all we had to do was go and buy it. We want to examine, say, Google and their web apps internally. We can't do that. We can't just go and buy a Google server and start playing about the code on it. But this brings some interesting attacks that we can do. So this is an actual piece of paid work that we did recently. That's a VoIP claim. Pretty standard thing.
How many of you got VoIP claims in your office?
Quite a particular one.
That
particular one. Amazing. Wow, excellent. I'm very interested on this bit then.
I'm not going to pick this device. So, the customer said to us they want us to recover the certificates that are used to provide access to their network off this device. The scenario was that the device was installed.
So they've got, is it right in thinking they've got network access control on their network? So they've got a nice secure network, you have to have a certificate in order to be able to get an IP address on your network. So they want to know whether we could recover that certificate from the device.
So we thought, well, we'll give that. Why? Well, because no one's going to call the police if you nick their phone off their desk. They'll call technical support, who will probably bring you another phone and have a bit of a laugh at why someone's nicked a phone off someone's desk. So we didn't really succeed with any kind of software-based attacks. Now, most of these devices use solid-state memory to store their firmware. These are the kind of chips they're stored, called NAND flash. It's a 64 megabyte chip or something on the device, and it stores everything, the firmware and all of the settings. So the attack we went through was we desoldered the chip off the board. So we took the device apart, used a hot air tool to take it off, and then I put it in this little reader. Now this reader is actually based on something used to hack PS3 DRM, the digital widescreen PlayStations. It's just been repurposed to work for other devices. We can do this with other devices. This is another little memory chip on the device we can clip into it and read the contents out of it out in situ. This is a digital video recorder, and we've got loads of things going on here. We've got a memory chip here with a test clip on it that we're trying to read the firmware off. We've got a serial device here connected to the serial port so we can see what's going on. Again, it's to recover the firmware of the device. With the phone, we used a little utility to dump the firmware, so it was actually quite good. So it's 256 megabytes, so a big flash chip for a phone. We ran Binwalk on it, that same utility we saw earlier to work with the camera. And we can see we've got strings coming out, Polycom, XML, things like that. So we know we've got a good dump of that chip. We didn't actually manage to recover the file system completely because they use a custom version of something. But what we did was we found in memory the private key. So we could read the key off there. From that point, we could use that on a device to connect to that customer's network. So it's an interesting attack. You can protect against it. You can encrypt firmware. You can encrypt devices. You can put tamper resistance on it. Is it required for these devices? Not really sure, but it's just the kind of level you can go to when you want to do these kind of things. Now, at the moment, most people are just messing about with IoT. I don't know if you've seen this. So you know these big road signs that line the road, you can change them. Now some of these, just a disclaimer. Obviously, I've never done this, and people would testify to my character that I wouldn't have done things like this. Some of them you can just open the little box and there's a keyboard in there, and you can type in a new sign. But lots of these use RF to communicate with them, and people have worked out, reverse engineered it, and worked out you can change them. So most of the time people are doing funny stuff like this. Now this one's brilliant. This was 2 or 3 years ago. There's a search engine called Showdown, and if you haven't used it, go to it and have a play about it. It's a search engine for the Internet of Things, and it's very different to Google. What I did was I spent a lot of time on Showdown trying to find vulnerable devices, and I typed in, can't remember what it was, but I found pages like this, Prism View Player, with this really strange long image on it that changed in sort of 15 seconds. It didn't take long to work out that these were billboards, big electronic billboards. At the time there were several hundred of them on the internet, and there was no access control whatsoever. So this is the view page. Simply appending a page to the end of the URL will allow you to change the images on these devices. I tried reporting this. The company said no one would possibly exploit this. Someone else was a bit more persistent and eventually got them to respond. But not before someone put a very, very, very rude image up on the billboard. Now, some of you probably know what that is, just speaking from the pixelated view. It's not pleasant. It actually hit the news. It was on the BBC News. It was that big by someone changing this. It's just people messing about at the moment. The thing is now that we're starting to integrate these things into our homes, into industry, and as people kind of do this, they're getting more and more valuable targets for attackers. And one of my big fears is that nation-state attackers are going to start attacking IoT devices in the UK. It might sound a bit over the top. 5 years ago we were talking about default passwords on DVRs, building a botnet, and it sounded over the top back then. 5 years on from here it happened. I don't think it's completely ridiculous that if there was a vulnerability in something deployed across 100,000 of them in the UK, that another nation would start attacking it. So just to wrap up.
How are smart meters looking?
Smart meters?
Yeah.
Do you do you want my honest opinion?
Yes.
I think smart meters in this country aren't too bad. So if you look at other countries that have had problems with smart metering, if you look to Spain, they made a massive mistake. Every single device had the same AES keys. So someone took 1 meter, took it apart, recovered the keys, which was quite difficult. Once they got that, they had full access to the backhaul infrastructure. We're quite lucky in the UK, so CSG and GCHQ have all had their input into smart metering. We've got quite a good organisation called the DCC that deals with all of the backhaul communication for the meters, and they really have thought about how to secure them. Everything's got its own key. The backhaul network's completely segregated. There's so much monitoring in place to prevent anything serious happening. The thing that I don't like is that every meter's got a disconnect in it. So even if you don't know it, even if you're not on prepay, every smart meter can have the power of disconnecting remotely. I don't think it's likely to happen by an attacker, but anything's possible. So that's my opinion on smart metering.
We have actually tested smart meters, but obviously I can't kind of go into detail because we did it for clients, but yeah, we've done quite a bit of testing in the past. Which might explain why they're a lot more secure than perhaps in Spain.
I didn't really test it.
No, you didn't. No, it was slightly before your time.
Yeah, with smart metering, one of the things that's starting to concern me, these boxes called CADs, consumer access devices. So they're like little gateways that bridge between the internet and what's called the smart meter home area network. The idea is this takes your smart meter readings and sends them through to the internet, there to be used for you to monitor energy consumption, and also for comparison sites, so if you want to change your tariff. The problem is that some energy providers don't like the fact they only get daily readings off the actual smart meter, so they want to use CADs to take more frequent readings, so every minute get a meter reading sent back, and then that gets a bit scary because they might actually start acting on that rapid data. If somebody's controlling generation, acts on that data. The other thing is these CADs are like this, they're little boxes running Linux sat on your network, and if there's 100,000 of them out there, they get attractive targets. Just to wrap this up, we have gigs at IoT all of the time, but it's really important to notice that no one's set out to build horrible devices like this, or to deploy insecure things. What they wanted to do is they wanted to get something that worked. They probably didn't have enough budget for security. It's really, really easy to make these mistakes. We get customers come to us to secure IoT devices, and they clearly thought about security, yet we still find problems. And they're the guys that are willing to take that extra step to come to a pen testing company. If you think of all the startups, all the new internet companies out there who aren't getting this testing done, it starts getting a bit scary.
Cool. I think that's it. I guess any questions? Yeah.
Naively perhaps, but doesn't your last comment perhaps say that what always used to be done, let's not call it a firewall, but you hub in some safe form and you create an invisible wall behind that so you can't get to these devices. To actually have every one of those passing the test, etc., you're never going to get there, are you? Because too many devices are going to come out. Surely there's a need for a device to protect it specifically, rather than relying on everything we relied on data transfer in the past and data processing, which is a different world, as you started saying.
So essentially, what you're saying is there a need for some kind of device to protect the devices? Is essentially what you're saying. Well, I think is it?
There's Cujo.
There's a company who decided to come out with an IoT firewall, or whatever it is. I can't remember the name of it, and I think that's got its own problems as well, which which does lead to a potential challenge. I think the bottom line is that as most consumers, there's very little you can do. You end up kind of being like Andrew, where he's got totally separate networks, completely firewalled off from absolutely everything, with loads of monitoring, just so that he can turn his lights on and off from his smartphone. And it's just the reality is, it is not going to happen. And I don't think that's where the fix needs to come from. I personally think the fix needs to come from the manufacturers in the first place. And then the likes of the IoT-SF, the IoT Security Foundation, are hopefully going to kind of drive standards within smart devices. How that's going to work at the moment is very much you've got to sign up to it. It's a self-certification thing. I think what really needs to happen is we need to get much more emphasis from, not necessarily from government's work, but from organisations to say, I'm not happy with that. There has to be a mandatory requirement to do any form of testing before you put something live. When a company builds a website that they put live, for example, most companies, certainly large companies, they're not going to put that website live without doing any form of pen testing. It's almost like there's a culture that you have to do that testing. That culture, I don't think, exists in smart devices. And I think that needs to change, in my opinion.
The thing is, even the companies that come to us that are testing these things, we're testing devices as they're coming to market. So really, pen testing of devices like this needs to happen from the beginning. We need to be involved with the security architecture of it and so on. So we're still coming in too late, but we're gradually chipping away and coming back.
That's always the problem, though, isn't it? Even with standard pen testing, we invariably come in after someone's built everything, and after about 10 minutes before they want to go live, usually, a couple of weeks before they want to go live, and And that's the challenge, you know, really to do security well, as you know, most of you will know if you're security professionals, you've been banging on for ages, you want to get involved at the development lifecycle stage, the development stage, and it's exactly the same in IoT, I think. Wow, 3 questions in a row. I think he was just first.
Isn't the problem with the utility devices, your cameras and things like that? Basically, people want to sell them for £100 a time, not £120 a time. So they leave out a stage in the development of doing the development and then producing a production version of that doesn't contain all the bits that Andrew says it shouldn't contain. And it's much easier for them to load the firmware from the development version and ship it out. We might just have to pay another £20 for our camera.
So in short, it is cost the deciding
And
factor in terms of
probably
putting
time to market.
Yeah. I think so. You know, especially when you think about certainly the people who are sort of kickstartering releasing their products. You know, the people who do that, they've got one product. It's the only product they've got. So they need to get to market quickly to start making money back, and so those corners are cut. But at the same time, the premium that you're paying for those devices, you know, the Wi-Fi kettle that we had a few years back, which I'm sure you've probably seen the article on, an absolutely abysmal piece of equipment. That was a normal kettle. Yeah, it had some nice functionality in that you could have different temperatures. They were sold in China without the Wi-Fi functionality for around about £60. So it's quite an expensive kettle, but it's a good kettle nonetheless, right? They stuck the 50p Wi-Fi module on it, doubled the price of it. So I do think there's certainly some money there that they could use for testing, but the reality is a lot of these companies are very much just building one device. You know, the Samsungs of the world, I don't think that they should. I think they need to be spending a lot more of their money on it. But you know, the new single product companies, I think you're going to have a hard time getting them to do that.
The thing is, what's the penalty to them? You know, if a breach doesn't happen, they don't really pay anything. And I know right at the beginning I showed the Amazon thing, it was like 2.5 stars, but that's because the cloud functionality doesn't really work very well. It's not a security problem. It's so much this IoT stuff. And I'm not sure if you've seen the Twitter account Internet of Shit, which is just full of rubbish that people create. So much of it doesn't work. I've never got the Wi-Fi kettle to boil using my phone. I have managed to boil it using Telnet and my laptop and an email attack. You know, it all gets a bit confusing, but just so much of it just doesn't work. So it's not just security and stuff.
I think that chap was next, and then your friend at the front as well.
The point I was going to raise is exactly when you just raised, which is what's the penalty? And it seems to me that nothing's really going to change until one of two things happens. One, there's some national catastrophe, which means there's regulation, and it would have to be pretty draconian. It's not obvious how that would work, actually, because a government's legislatures are not particularly good at regulating technical stuff. The other possibility, and again the law would need a bit of development, is a massive liability to use that way. Because if you ask yourself a rhetorical question, if you have some lousy IoT device which allows a huge botnet to come in and totally bring down someone's infrastructure, why shouldn't you be liable for that if the cause was your complete failure to make any sensible steps to secure?
So, I mean, looking at Mirai, Mirai is quite interesting. So many of the impacted devices, we can't find who made them. So we've probably got 6 DVRs now, digital video recorders, that are vulnerable to Mirai, and I think only 2 of them, we can tell who made it. One of them we know who we bought it from in the UK, but we've contacted them about the vulnerability, and they can't appear to work out who actually made the firmware that goes on the device. So what's worrying is that 2 of these people were big brand names in the UK, making DVRs, and they weren't aware that DVRs were vulnerable to Mirai 3 weeks after Mirai started. So no one in there had thought, hang on guys, we sell these things, should we see the helmets open? Should we try logging in using these credentials? They didn't try that. So the problem is, like, who would be liable? So much of this stuff comes out of China, it gets white labelled, it gets rebadged. It would be a difficult thing to solve. I mean, I agree, maybe GDPR, if the data breach was, if a European company actually lost data as a result of an IoT security breach, they could get fined.
We are seeing a little bit though. I'm sure you've all seen My Friend Kayla, our little doll that we've had. Well, that one just recently, an organisation in Europe actually put out a thing saying, this is totally unacceptable for children to be using this device. And in America, we're starting to see them saying the same thing about that particular device. And sooner or later, there's going to be litigation as a result of a poorly designed device. Whether that's going to change all of the devices, probably unlikely, because someone will white label, as Andrew said, someone will white label something in China, and who do you go to sue? It's going to be the big manufacturers, fine. Maybe Samsung will get sued at some point. And we saw actually interestingly with the TV recently, it was in the news recently, the Vizio TV. Although it's not necessarily a hacking thing, it's more of a privacy thing where effectively they were tracking everything you viewed, every single thing you viewed, and uploaded it to their servers and then sold it to advertisers. They've just been fined $2.2 million by the FCC, and you can bet bottom dollar is going to be a massive amount of litigation to follow off the back of that. But that's just a TV manufacturer who did a privacy breach. Probably, are we going to see that with some white label product coming out of China? Unlikely. I think there's another question as well. Was it?
A follow-up to that, I guess, that how much of this stuff is really unique once you take the outside packaging off? Because companies coming up with more and more reference designs and stuff like that.
Yeah.
Is it that there's a handful of people producing reference designs?
I think that's quite a big
So how to
yeah, are these do these devices share a common heritage that means that we're seeing vulnerabilities spread across multiple manufacturers? And I think we are seeing that. So when you get a device like this, I can't remember what chipset this runs, but you get something called a board support package that will come from the chip manufacturer or possibly the board manufacturer. And you'll be able to build firmware around that. Quite often they have issues, right at the outset. So when you start building it, you already have issues. There's binary blobs sometimes in these that have vulnerabilities in them, so you can't even see the source code. And if you look at the DVRs, most of them use a chipset called Hisense, I think, High something. A particular chipset. Again, we see commonality between the firmware across 30 different manufacturers. It's not all the same, but the same vulnerabilities exist across many devices, which is quite a scary thing.
Take one more question.
You'll say it all.
I'm a bit worried now. Driverless cars?
Yes,